In this problem, we need to find the magnitude of the velocity v1 for which the maximum angle to which the block will rotate is 30 degrees. So I have here a sketch of the problem. So you can see here the dimensions and the velocities. So what happened is, a rectangular block of mass m initially traveling at a constant velocity of v1 hits point B. So the impact produces an impulse at point B and causes the block to rotate with angular velocity omega 2, so you can see in the last part of the diagram, and its mass center to move with velocity v2. So before we write the equations, let's first do some conversions and initial calculations. So the dimensions of the block, so A and B, are in millimeters. So converting these to meters, so we'll have, so A is equal to 200 millimeters times the conversion factor. So 1 millimeter is equal to 10 raised to negative 3 meter. So cancel millimeter. So we'll get 0.200 meter. And then for B, so B is 100 millimeters. So multiplying it again by the conversion factor, 1 millimeter is equal to 10 raised to negative 3 meter. So that would be 0.100 meter. The moment of inertia about the mass center based on its shape is given by, so I equals 1 over 12 times the mass times the sum of the square of the dimensions, so times a squared plus b squared. The distance from point B to the center of mass G, as you can see in the last part of the sketch, is D. So it's given by, so D is given by, so D equals, so this is actually 1/2 of the diagonal, so 1/2 times, so square root of a squared plus b squared. So calculating its value, so this is equal to, so 1/2 times the square root of 0.200 meter square plus 0.100 meter square. So you'll see that D is equal to 0.1118 meter. There, so those are our given values. Now, before the impact, the velocity of the block is v1. And since there's no rotation, omega 1 is equal to 0. Now, after the impact, the block rotates about point B with an angular velocity omega 2 in the clockwise direction, and v2, since we know that the linear velocity can be expressed in terms of r and omega, so v2 is equal to, so v2, let's write it here, v2 is equal to, the r is d, then omega 2. There. So, applying the principle of impulse and momentum and taking the moments about point B with the clockwise direction taken as the positive direction, so we'll have mass times V1, then V over 2, because the center G is at a distance of B over 2 away from point B, then plus 0 equals, so I omega 2 plus md times v2 or mv2 times d. Okay, so replacing I with the equation for the moment of inertia and replacing v2 with the equation for v2, which is d omega 2, this equation becomes, so m v1 b over 2 equals, so 1 over 12 times the mass a squared times a squared plus b squared omega 2 plus, so m d times d omega 2 is m d squared omega 2. So substituting the equation for d, so that we got earlier, so 1/2 of the diagonal, so this equation will becomes, so m v1 b over 2 equals 1 over 12 times m times a squared plus b squared omega 2 plus, so this will become, substituting the equation for d, so 1/4 m a squared plus b squared times omega 2. So simplifying the equation, so this becomes m v1 b over 2 equals, so 1/3 m times a squared plus b squared times omega 2. And then finally, so omega 2 is equal to, so b over 2 times v1 times 3 over a squared plus b squared. So simplifying that, so we'll get, so omega 2 equals, so 3 v1 b over 2 a squared plus b squared. Okay, so let's have this as our equation 1. So the value or the expression for omega 2. Now, the motion after the impact is a rotation about point B. So I have here an illustration of what happens after the impact. So at position 2, so we have V2 is again equal to D omega 2. Then at position 3, as you can see in the figure, the block rises for a height h and makes an angle of 30 degrees with the horizontal. So because that's the condition in the problem. So as you can see, we have here an angle, so beta. So solving for beta, so beta here is, so we'll use the tangent. So tangent beta is equal to b over a. So beta is equal to arc tangent of b over a. So that would be arc tangent of, so 0.100 meter over 0.200 meter. So this will be equal to 26.57 degrees. So we'll use that in our calculation later. So beta is equal to 26.57 degrees. Now, so we don't know the value of h, so we can solve it. So solving for h, so h is equal to, so it's equal to Okay, so half of the diagonal. So that's d times sine of the combined angle beta and the 30 degrees. So sine beta plus 30 degrees. There. So solving for h. So earlier we got a value for d. So 0.1118 meter. And then times sine. So 26.57 degrees plus 30 degrees is 56.57 degrees. So this would be equal to 0.0933 meter. Okay, so that's the value of our H. Now, applying the principle of conservation of energy for position 2 and position 3, so we'll have the equation. So U, the potential energy at position 2 plus the kinetic energy at position 2 equals the potential energy at position 3 and the kinetic energy at position 3. So let's substitute the values. So the potential energy at position 2 is, so the center is at a distance again of b over 2 away from point B. So that would be, so mgh, so h is equal to b over 2. So b over 2. And then for the kinetic energy, so since it's rotating at an angular velocity omega 2 and the center of mass is moving at velocity v2, so the kinetic energy at position 2 is equal to, so 1/2 I omega 2 squared plus 1/2 mv2 squared. Then for the right hand side, so since the block rose for a height of h, so the potential energy is mgh, and then our kinetic energy here is 0. So again, using the equation for v2 or substituting the equation for v2, this equation becomes, so mg b over 2 plus, so this can now be, and this can now be, so 1/2 times I plus the mass times d squared, because of v2 is d omega 2, then multiplied by omega 2 squared. So equals mgh. So substituting the equation for I and D, so this will become, so mg b over 2 plus 1/2, let's put omega here, omega 2 squared times 1/12 times the mass times a squared plus b squared plus, so 1/4 m, this is for D, so a squared plus b squared equals mgh. So simplifying the equation, so this would become, so mg b over 2 plus 1/6 times m times a squared plus b squared omega 2 squared equals mgh. So further simplifying our equation, so this would become, so 1/6 m, so a squared plus times a squared plus b squared equals, so mg, this become h minus b over 2. So omega squared here. Okay. So, from here, we can get the equation for omega squared, omega 2 squared. So, let's just get the square root later on. So, this is equal to, 3g times 2h minus b over a squared plus b squared. So, substituting the values that we have, so that's 3 times 9.8. I'm omitting the units for simplicity. So, 2 times 0.0933 minus 0.100. Okay, all over. So, 0.200 squared plus 0.100 squared. So, omega sub 2 squared would be equal to 50.9208 radians per second. And then, getting the square root, so omega 2 is equal to the square root of that, so 50.9208 rad per second. So, it will be equal to 7.14 radians per second. Now, so, using the equation for omega sub 2 earlier, equation 1, we can solve for V1 since we already know the value of omega 2. So, equation 1 is, so let's write that first, omega 2 equals, 3v1b over 2 times, a squared plus b squared. So, deriving v1 from here, so v would get, v1 is equal to 2 times omega 2 times a squared plus b squared over 3b. So, substituting the value, so 2 times, again, I'm omitting the unit, 7.14 times 0.200 squared plus 0.100 squared all over 3 times 0.100. So, you see that V1 is equal to 2.38 meters per second.